Hi everyone, welcome to this video series on essential statistics, a primer for data science and machine learning. As usual, the focus here will be on foundational concepts along with examples, use cases and applications, do's and don'ts, and also Python demo. So today we'll talk about data distribution, which is a very important concept in statistics. Let's get started. So understanding data distributions is very fundamental, and it involves familiarizing ourselves with many of the fundamental concepts on data distributions. Some of the data distribution that we will start with, or rather we focus, will be the normal distribution and uniform distribution in this particular video. The normal distribution, as you know, is bell-shaped normal distribution and characterized by symmetry or symmetrical shape. We'll discuss whether we really need the data to be symmetrical or not symmetrical from machine learning and data science perspective. Uniform distribution is uniform. That means all values are equally probable. So let's move on and see some of the useful and important aspects about normal distribution, like probability distribution and probability density, cumulative probability density, and so on and so forth. And this video on data distribution also has significant amount of Python examples. So what is data distribution? It refers to the way the values or outcomes are spread or present in a data column or data series, or how the data is distributed in a data column. And that provides information about possible values a particular variable can take and how frequently those values can occur. This is important analytics that we conduct on any data column or data series. So understanding distribution of data is fundamental to machine learning, deep learning, and in fact, any of these statistical projects. And that allows us also to choose a proper or or a better method to do the analysis like machine learning or deep learning. So let's look at some of the examples of data distributions that we hear about or probably we know about. The first one is the normal distribution, and it is characterized by symmetry, commonly seen in the numerical columns like height, test scores, blood pressure, or temperature, humidity, wind pressure, or atmospheric, all the weather-related data mostly, they follow a normal distribution. One more distribution that we commonly hear about is uniform distribution. And in this, all values in a particular range is equally probable. That means if you have a range of, let's say, 10 and 20, so within 10 and 20, any value is equally probable. And that means it's typically a straight line in terms of a probability density. We'll talk about the concept of density in this distribution. Next one that we see also commonly is left skewed data. That means the values on the left-hand side here on this side will be some values might be present on this side. So this is also called negatively skewed data, and it has a tail extending to the left. For example, income distribution, where high earners are typically very few, and most of the earners are on the average side. So this side could be your high earners. Another example would be just opposite of that, which is the right skewed distribution, where the right side is skewed, and this would be commonly seen in let's say the products where the failures occur, and the lifetime of such products, will exhibit this kind of a pattern. That means the product which have defects, they will typically be lasting for fewer days, and most of them will show this pattern. Some of the products where the defects occurred may last longer. So that is why the tail is extending. So this is skewed on the right hand side, and this is called positively skewed. Now, this right skewed and left skewed is closely associated with, the normal distribution data that is very common in analytics. Some more example of data distribution: exponential distribution, where the values are exponentially decaying, and mostly it is applicable in queuing theory. One more example, binomial distribution, where we are looking at number of successes in a given number of trials. And for example, Bernoulli trial, and that shows this kind of distribution. In this video, we will focus on normal distribution and uniform distribution, to be precise. So how is data distribution really different from the dispersion method that we talked about in a previous video? So let's try and understand that. So data distribution is about how the data is spread or distributed in a data column. Dispersion also talks about the spread, but more in terms of quantifying it and the variability of values within the data from the center point. The focus of data distribution is to understand or concentrate on frequency where the most of the values happen or occur. Dispersion method, here the focus is to what extent the values are deviating from the central point. Some of the characteristics that we will be studying here in data distribution would be probability densities, skewness, symmetry, and kurtosis. Whereas in the dispersion method, we talked about range, variance, standard deviation, IQR, and so on and so forth. So the here we are more focused on the overall scope, the shape of data, and here is about variability of the values. Data distribution is mostly qualitative, whereas the dispersion methods that we saw earlier, they are numerical representation in terms of, let's say, mean or range or standard deviation or IQR, right? Q1, Q2, Q3. So that's the perspective here. Now, before we move on, we have to understand a couple of, topics from mathematics. One is integral. We will keep the discussion more at the intuitive level than rather performing the, integrals here. Let's say the function is x squared, which is kind of a quadratic function here. And we are interested in finding the area defined between the point 2 and 3 and the area under the curve. So how do we do so is by computing the integral or definite integral of the function x squared between these two values, and that is called area under the curve. So the definite integral is nothing but the area under the curve in that region that we are specifying here. So this is called integral, and how we do so or how we compute, I'm going to show you in the next slide. So what is the correlation between the definite integral that we are talking about and the probability or probability density? that is associated with data distribution. The correlation between the definite integral or the area under the curve, so this is the definite integral, and the correlation between that and probability is typically seen in the probability dense distributions for continuous variables. An area under the curve, the probability density over a particular interval is actually the probability of the random variable x. So that means, let's say the variable is this one is your variable, and the function can be anything, and we compute the area between this point, and the point is, let's say, 2.1 to 2.2. So roughly about, we are saying 2 point in between, the average of this. So what's the probability of that point? So the probability of, let's say, 2.1, 2.2, and that's 4.3. So divided by 2, that's 2.15. The probability of 2.15 will be this area here. So this is the correlation between the integral or the area and a particular value. Now we are talking about continuous, variable where the variable can assume infinite values. And then it's very hard to compute the probability of a specific value the variable can take. So the approximation that we take is, or we make, is we take a small region around 2.15, lower, slightly lower on the left hand side and slightly more on the right hand side, and then we compute the area by using a Python function. So this is a correlation between the definite integral and the probability in case of probability density function. So let's take an example here. Let's say we have a column, and the column has a mean and standard deviation as parameters. So the objective is to compute the probability that the random variable x lies between 2 points A and B, and that probability density function for a normal distribution is characterized by the famous formula here, where the mean and standard deviation is used for that column. X is individual values in the column. So essentially, for every value is going to return the probability density function. So what this function actually does is the following. Let's say this column has the minimum of 100 and the maximum value is 200. So this end is 100, this end is 200. And if we take, let's say, in between 10,000 points or 100,000 points, and then for each of the point we apply this, we're going to get a curve like this. This is the meaning of this function, and that's what we call as probability density function or representation. So for each point, we are going to get a probability density function here. So this probability density function simply means a neighborhood. Let's take another point here, and let's say this point is corresponding to that. So what we're going to do is we take a small area or a region around this point, and the area under this curve is going to be synonymous with the probability of this particular point. So typically we take a region, around this point as a very, very small region, and then we compute the integral. That integral represents the probability. or probability density. We'll talk about what is the intuitive meaning of probability density. So the calculation of probability density is essentially integral, and don't worry about all these formulas. We are going to use the package. The intuition is make sure use the right range and then use the function and call the Python packages to compute the definite integral, which is nothing but the area between A and B. So let's look at some examples of probability density function that so right now we just talked about this one. Uniform distribution is very easy, which is like the value between A and B. So all values between A and B are equally likely. So for that equally likely, the probability is simply going to be 1 over B minus A. And that's the famous uniform distribution. Similarly, we have exponential distribution. We'll talk about that, these specific distribution in another video series. But in this particular video, we'll talk about normal distribution and uniform distribution, along with the examples where we use them. And likewise, the binomial distribution and the Poisson distributions are very popular examples of probability density function. Each one of them will have a different shape of the curve. So let's look at an example one here. Let's say the function is x square, okay, and then that's the function, quadratic function. And the area under the curve, which is let's say 0.2 and 3, that gives the probability density, which is equivalent of the area under this or in this shaded region. So, in other words, this probability or the area also gives you an idea of how likely is this point. We'll take some more examples to illustrate that useful data analytics that we can perform with such measures. Okay, so this is what will be our point of interest from now on, the area under the curve, and why this is called probability density and what are the use cases of probability density. So the calculation, let's take one exercise, PDF calculation. We're not going to do, coding as such, but I'm going to show you the library which you can use. So given the probability density function, let's say the function is 1 over 4 multiplied by x squared, and we have to calculate the probability that x is between 1 and 2. Essentially, we need to find the area under the curve over the range of 1 and 2. So that's what it means here. So let me show you. So this is the function, and we are interested in this range, which is 1 and 2. And then the area is the light shaded region. So we need to compute that probability. So we use the SciPy library to compute the area under the curve, which is basically one-liner. The SciPy library is called quad, and in this we will pass the function. So let me illustrate as to what is happening. So we're going to pass this function here, and then we pass the range, let's say A and B. For example, 0.1 and 0.2, and then essentially it is roughly here we are talking about 0.2 as the point. I've taken a small lower limit and a very small higher limit or upper limit to zero point 0.2. Just added 1 here. So that's it. This is what we do to compute the density or area under the curve. So let's look at some examples. What would this mean here? So there are 3 points here. Let's go through each one of them. So this video is going to be slightly longer, and I'm going to use lots of examples to make it clear. I hope you guys will appreciate and the finer points here. So there are 3 points here. Okay, so one is around the mean. The mean is this. The red line is the mean, which is equal to 1. Okay, so at this point, so this is the mean of the data series. Now, around the mean, we have the probability density equal to 2.5 multiplied by 10 to the power minus 6. So what does it mean? It means the probability density around the mean is low, of course, is low, but now we're going to talk about um, in terms of relative sense. Is low within the narrow interval, so I use this interval here um, to get to 1. So you notice this is very close to 1 and this is also very close to 1, just a tiny difference. This density is small, which is this one, is pretty small, but it is not 0. You notice it's not 0. So that means some probability of the mass. That means this is the likelihood that the column likelihood that a column will have the value equal to 1. This is what it means here. Let's look at another point, which is 0.8, which is about this red line here. Okay, this red line that you see here, that's 0.8. Now, what's the probability density? I got this probability density by using the range 0.799, which is also close to 0.8, and then 0.8001. This is also close to 0.8. Now, this small array value suggests the concentration of probability density, means some area. So this is representative of the area, under the tiny curve, tiny region, or under the curve here. Okay, so that's the area here. So, and this is also likelihood. So likelihood that the point or the column will have a value x equals to 0.8. Let's compare the two. Here, this one and this one. Notice which value is higher. The value, around 1, the probability density is higher. That means it's more likely that the column will have a value of 1 than column will have a value 0.8. That's what it means. Let's look at point 2 here. Point 2 is very close to very small point here, point 2. And the probability density that I got is 1.0 10 to the power minus 7. And you can see here 10 to the power 7 is smaller than the previous two. So the interpretation is again the probability density around zero point 0.2 is very low. In fact, this is lowest of the three. Okay, so lowest of the three. That means the probability that the x will be equal to zero point 0.2 is lowest. And the highest is probability where the x is equal to 1. That has a highest probability among the three. So these kind of analytics you can perform as part of your data science before you begin machine learning exercise. I hope this is clear. Let's move on then to the some more examples here. Okay, so let's move on here. The exercise 2. Now, we talked about PDF and there is something called CDF. Okay? CDF means cumulative density function. So why we need this? So let me illustrate again. So when you computed, let's say this is this function fx equal to whatever, and that's my x-axis, and then we can compute the probability density for each of the point. I'm not drawing the region. You can now make an assumption. Every point is actually a region, very small region. Now, each point is nothing but PDF, and that has a sum. So that PDF is nothing but some numeric number or like area under the curve. So each of the point is that. Now that's not probability, right? So each of the point is simply likelihood. They are not probability. So let's say this point is 2. Okay. So what's the probability that x will be less than equal to 2? Right. In that case, we need to take all of these uh, densities, and then let's say this is 2. So we take all of these and we add them up, and then we get whatever we get. That's the probability. Let's say 0.74. So when we add this, this is called cumulative density function. So now we can use the PDF from the previous exercise that we did, and then we compute the cumulative density function. Essentially, the PDF, just for illustration, this is what we just did in exercise 1, where fx equals to 1 over 4 and x square, and that's the function. And each of the point is nothing but your PDF. Now, when we take all of these points and cumulatively we go on adding, then we get a increasing probability curve, and this is called CDF. This is useful in determining the exact probability of a particular value. So the blue curve is the PDF, and the green one is the cumulative density function, and it starts from 0 and approaches 1, because probability is going to be 1 anyway, right? Cannot be more than 1. Now, steepness of this CDF indicates the rate at which the probability is accumulating. So in fact, this is what we will use, or Python packages use CDF internally to return the probability whenever we ask for probability. So how do we convert a PDF to CDF? I think I already illustrated the finer points. Let's look at it one more time. Now this time the function is different. It is e to the power minus x, which is exponential, but in the opposite way. So in this case, something again I'd like to highlight some of the main points. So at the blue curve, at this point, you will have the maximum PDF. And as you go down all the way, so the x is assuming higher values. Let's say x equals to 2, 2.1, 3, 3.1, 4, 4.5, and 5, and so on and so forth. As the value of x is increasing, the PDF is decreasing. So it means the likelihood of the function where the variable is taking higher values, it is going down. That's what it means here, the PDF. So when you cumulatively add them together, this is how it will look like, and at the end it will remain constant. Like, it doesn't matter, because the probability is very, very negligible at this point, and hence this is on the top end of the CDF is high. That's what it means. Now, the interesting thing is the densities are more for lower values of x, which we just described. Look at the red line. That red line means the maximum density at x is equal to 0. That means when the value of x is equal to 0, e to the power 0 is 1. So that's what it means. But the probability is low. Okay, so now why would we say so? When the density is high, but the probability is low, right? Why we say so? Let's look at another conceptual point. Now, density simply means the concentration or area or likelihood at a particular specific point in a continuous distribution. So in the context of PDF, fx is a function and the higher density at a point indicates the greater likelihood of that variable taking that particular value or near that value. Now, probability calculation is all about cumulative. The probability is not just the density that we spoke about, but also the width of the interval. That means you're asking about the probability of 2 means, less than or equal to 2. So that is called the width of the interval. So for continuous distribution, the probability is computed considering the density and also the width of it. And so what is meaning? Meaning is this. If you look at the cumulative one, so when we say probability of 2, this is what it means. All of this area here is the probability of 2. In the density is just the specific point here. So density is just that point, whereas the probability is all of it under the curve, right from the lowest point to the point of interest. So for probability is not just the density, but also the width. This is what it means here. All right, so the for this particular case, exponential distribution e to the power minus x, as x is increasing, the density is decreasing because of the exponential nature. And but simultaneously for the CDF, okay, the interval is getting wider, and that's how the probabilities will change or increase. The overall probability is influenced by both the density and the width of the interval. So it means the probability that it will be 1 will be lower than the probability that the variable will have the value 2 or 3. So as you move to the right hand side, the probability is going to increase. All right, so let's then use these concepts for some more examples. So finding the probabilities from CDF. Now that's what is going to be used. So CDF is used to return the probabilities to us. So how to find the probability from cumulative density function? The CDF provides the cumulative density function. Let's say we are interested in probability that the value is less than 2, and that would be the point here, and that means the area, all of these PDF here, you add them together, and that's going to be the probability. Essentially, let me just one more time. So here, this is nothing but the PDFs and addition of all the PDFs. So let's say here, and we computed the PDF for each of the point, and then we add it. So this point that you see here is nothing but the addition of all the PDFs here. So this 0.86 is nothing but when you add all the PDFs here, that returns 0.86. So that's the use of CDF, cumulative density function, to get the probability. So the interpretation is point A, let's say x equals to 1. So essentially we are saying CDF where x is less than equal to 1. Similarly, for 2, less than equal to 2. For 3, less than equal to 3. I hope this gives you a clear picture in terms of what is density, probability density, and what is probability. Let's talk about now implementation of whatever we have talked about in uniform distribution and normal distribution. So the probability density function, recap, it describes probability density, describes the likelihood of the random variable at that point very close to a range. It does not describe the probability as such. So PDF provides a way to model the probability densities or likelihoods. And when you convert that PDF to CDF, cumulative, that's where you can draw the probabilities. Let's look at the uniform distribution. This is how you compute the probability for uniform distribution. Quite simple. Let's say point A and point B, and that would be the probability of every point between A and B is going to be 1 divided by B minus A. And you notice here, any point you take here, the probability is going to be the same because that's uniform. We will see the examples of use cases where we use uniform distribution. So, what exactly is this data distribution? Simply, data distribution is nothing but the values, and these values are spread, and they are characterized by mean and standard deviation. So data distribution typically has central tendencies that we talked about it in the dispersion, variability, variance, standard deviation, and shape of it, symmetry, skewed, and all that. In this particular video, we're talking about the probability of values. So one more example of now the practical use case for densities. Let's say this curve represents your data point or data points rather, and probability density function at 20.2. So this is the green line here, 20.2. And then we have a probability density function at 30.2. And that is your 30.2 here region. Okay, so notice the small region I have drawn here. Okay, 30.2. So the PDF is 0.134. And the PDF for 20.2 is 0.106, and PDF of 60.2 is this one. Now the mean of my data series is 42, which is a red line here. So this is my 42. Okay. Now notice the value 30 is actually closer to the mean of 40. Okay. And the value 60, probably the green line here is 60 here, and that's a little far away from the mean compared to the 30. 30 is here. So the PDF, if you notice, the PDF for 30.2 is comparably higher than the PDF for 60.2. That means this column, the likelihood of this column taking a value close to 30.2 is higher than the likelihood that it will take the value 60.2. So this is the insight behind how we use these densities or probability densities to do analysis. So basically, the PDF value is higher for specific point in a continuous distribution. For example, here 30.2, it indicates that the probability density, not the probability, but probability density around that point is higher or relatively higher compared to other values. So that suggests that the values close to 30.2 are more likely to occur in the data series. For example, if you have 2 points, 25 and 30.2, the PDF of 30.2 is higher than the PDF of 25.0. That means the likelihood of the column taking the value 30.2 is higher. That's what it means. Similarly, for the lower PDF value, just the opposite conclusion you will draw. So the summary of this is the PDF provides a way to quantify the likelihood of the variable taking specific values in a continuous distribution. Higher PDF implies the higher concentration or higher likelihood. In other words, the area, you can think of an area under the curve or definite integral, while the lower PDF suggests a lower concentration or a lower likelihood. Now, the interpretation is quite relative. For one distribution, 0.13 could be different than 0.13 of another distribution. So it's specific to the distribution and the column. Comparing the likelihood of different values within a particular distribution. So we talked about it. Similarly, the curves that we saw so far, normal distribution, and one we saw was uniform distribution. So how do we get uniform distribution? Quite simple. Take the range A and B, and you divide 1 over B minus A. So the probability density function for uniform distribution is a constant because it's a constant value. And outside the range, the probability density will be 0. And the formula for probability density function is 1 over B minus A. So the probability density is simply a horizontal line in case of uniform distribution, 1 over B minus A. So that means each value is equally likely and total area under the curve will add to 1. Let's take a look at the Python example to show you the uniform distribution. Let's take a look at a simple example here. I'm going to take a lower bound 2 and upper bound 6. It could be any number. And then let's say I want 1,000 points between A and B. So generate those numbers by using NumPy and the uniform function. It's going to take the range and then it's going to generate those 1,000 points. And if you generate those 1,000 points and plot a histogram, you can see is almost giving you a very constant representation or like a rectangle. And visualize the PDF is going to be like a straight line because you're going to divide 1 over a particular scalar value. So this is the way we compute the PDF of uniform distribution. So that was a quick demo on uniform distribution and the PDF, how we compute that. Let's look at summarizing. The uniform distribution is nothing but a rectangular shape of the PDF for every value because every value is equally likely, so you get a rectangular shape. Some of the examples of uniform distribution, let's say choosing a random number between two values. Every value between the two values is equally likely. In that case, we use uniform distribution. Lottery number selection. Again, the winning numbers are chosen using a uniform distribution because every number is equally likely. Random selection from a deck of cards. Again, every card is equally likely. So you're going to use you're going to use uniform distribution. Let's say you have square and selecting a random point in a square. So every point is equally likely. So we can use uniform distribution. Random time of a day, again, is a very good use case for uniform distribution. Quality control in manufacturing, again, is, let's say, you are producing some products and just want to pick anything out of it. So or any product for quality control checks. So uniform distribution. Randomized experiments in any experimental design where you have treatments and experiments. Again, we have a use case for uniform distribution. Now we talk about the normal distribution. How do we get normal distribution? Essentially, a normal distribution is characterized by two parameters, mean and standard deviation. When the mean is 0 and standard deviation is 1, that's a special normal distribution called standard normal distribution. So the probability density function is computed by using this formula. We talked about it a while ago, and this formula is a Gaussian formula as well for normal distribution, and it takes the mean and standard deviation and the range of values, and it gives you the PDF for each of the value. And then when you plot, it gives you a bell-shaped curve. The shape of the distribution is typically bell-shaped, whether symmetric, non-symmetric, or little bit symmetric or skewed. It all depends on the data or data column here. So some more characteristics of normal distribution that we talk about very, very common is 68, 95, 99.7 rule. That means 68% of the data will fall within plus and minus one standard deviation in a normally distributed data. Approximately 95% of the data will fall within two standard deviation plus and minus, and three standard deviation will cover almost all the data. Now this is empirical. This is not a rule. Okay. So for example here, for standard normal distribution, 68% data will fall between plus and minus one standard deviation, 95% plus and minus two, and 99.7 is plus and minus three. This is very important rule, and we're going to use or make use of this rule in many of these statistical experiments, including hypothesis testing. So the basis of 68, 95, 99 rule is mostly empirical, or it is also called 3 sigma rule, more of a guideline than a rule. A rule is based on the properties of the normal distribution that we have seen over decades of experiment. So summary of say 3 sigma rule, bulk of data is typically within plus and minus one standard deviation, and approximately 95% would be plus and minus two standard deviation, and 99.7, that's like almost 100% of the data will be within plus and minus three standard deviation. Any data which is outside of 99.7 would qualify to be considered as outlier or extreme value. So where are the applications of normal distribution hypothesis testing? We'll talk about it. In machine learning also, we use the concept of normal distribution to scale the data. This is also we will cover in our data processing topic. In quality controls, the normal distributions are typically used to monitor the quality of production. Just a few I have listed. There are many other applications of normal distribution. Let's take a look at a Python code to show you the 3 sigma rule and how we generate the PDF for normal distribution. Okay, so let's take a look at a simple example on normal distribution. I'm taking a mean of 0, standard deviation of 1, and we're going to generate some normally distributed data. And if you plot the histogram, it's going to return the histogram, like there's the bars here. Now, to compute the probability density function, just use the norm, which is a package from SciPy. And this norm package will compute the PDF, which is basically the formula that I showed you earlier in the slide. For normal distribution, is going to return for every value in the X range, which we just defined it here, 100 points. And those 100 points, for each of the points, is going to compute the probability density. And those densities are being plotted in terms of a red color. You notice here the probability density PDF matching the histogram. Let's look at one more example here. And now in this example, I'm going to show you the relevance of the 3 sigma rule. Okay, so in this particular case, I'm using some widgets to show you this. I have a data series which has a mean of 170.18. So if you look at the plot here, let me reduce the size. So this is 170.18, which is basically the the green line, and here is your normally distributed curve. Okay, now yeah, I'm going to show you now 170.18. So this is the mean in the center, the green, and this is the PDF here. So now if I change the height to, let's say, 171, and you see the PDF is now shifting, and you can see it is, if someone, so basically it's about the height of adults in a particular city, and the average was 170 point something, and then I chose to make the point as or the height as 178. The plot is telling it's very unlikely that someone would be of this height, 170.40 centimeters, and you see it is beyond the PDF. So so that means here the PDF will be the highest around the center or the mean because of the normal distribution curve. And likewise, you can keep going to the right, and the probabilities or the PDF will be very, very small. And likewise, if you go on the left hand side, let's say someone is 156 centimeter adult, is very, very unlikely also. So that shows that in case of normal distribution, the data or the probability of someone or the variable being around the mean is highest. For example, here let's make it 170 again, and you will see that the probabilities are now, or the PDF is the highest towards the center somewhere here. All right, 170. So if I pick someone with the same height, then the probability that you will find someone with that height is very high. That's what it means. And this is the important concept that we're going to use in hypothesis testing as well. So that was the quick demo on normal distribution and PDF and also 3 sigma, rule. What are the examples of normal distribution? Quite a few. Height of a population generally exhibits the normal distribution pattern. IQ scores of some people, students in a class, or some population or sample in general, also exhibit normal distribution. Test scores again of select students or college within a class, that also, or SAT score, ACT score, they all exhibit normal distribution. Some more examples: errors in measurement. This also represents normally distribution or normally distributed patterns. Response time, psychology and the BPO industry, or the service industries, there also the response time of individuals uh, show the normal distribution. Financial market returns, that also shows normal distribution patterns. Blood pressure, measurement of noise, weight of manufactured products, SAT scores, for example, these all show the characteristics of normal distribution. So essentially, symmetry is one of the closely associated characteristics of normally distributed data. Bell shape, now whether it is completely bell shape or less than bell shape or skewed or not skewed, depends on the data that you have. Mean, median of a normally distributed data are equal because that's at the center. Standard deviation, larger the values of sigma results in the wider distribution, while the smaller values mean the narrower distribution. And another popular characteristic is 68, 95, 99.7 rule. So standard normal distribution also is called a variation of a normal distribution, and only difference is the mean is 0, standard deviation of 1 here is often written as Z. So normal distribution is normal distribution with any mean or standard deviation. Standard normal distribution is just the difference is the mean becomes 0, standard deviation becomes 1. So the use case for standard normal distribution is normalizing the data or standardizing the data. We will see those in our data processing. So let's say if you have a value, or let's say we have a column, so we subtract here by mean and then divide by standard deviation. So every data point now will be represented in terms of some standard deviation. This is called normalization. We'll discuss those in our data pre-processing techniques. Outlier detection is one of the applications of standard normal distribution because 99% of data will be within 3 sigma, and anything which is outside of 99% can possibly be an outlier. Hypothesis testing uses the concept of um, the 3 sigma rule. Some note on normally distributed. Not every data in the world is normally distributed. Although the central limit theorem says that data should be normally distributed. Examples of non-normally distributed: income distribution. Not everyone earns the same. There are people who earn quite a lot, and large mass of people earn typically common value. So this is an example of not normally distributed data or skewed data. Aging population is also an example of not normally distributed data. More people in the younger group than the people in the advanced age group. Product defects also show the patterns of non-normally distributed data. The number of defects found in the product typically follows another distribution called Poisson distribution, which is not normal. We will talk about the Poisson distribution in the advanced statistical topics. Some more examples of not normally distributed data. Web page hits. This also shows some patterns. Majority of pages are watched by majority of the users. Few pages are not watched by that. So again, tendency of skewed distribution. Customer transaction amount. Most of the customer, they have similar, small transactions, but some of them can do a large transaction. Okay, let's look at some more social media engagements. Some posts go viral, some posts do not go viral. Again, skewed data. Hospital duration, stay duration. Many patients stay for 1 or 2 days, and some people may need longer hospitalization. Wait times also shows some wait right skewed data. That means most of the time, people wait for very less time, but some time people may have to wait for longer time. All right, should we now? This is the most important point that we have in our mind. Should we worry too much about non-normally distributed data? Normal distribution is an assumption, a common assumption in many of the statistical method, but is also important. Not all machine learning models require the data to be normally distributed. So some of the considerations that I have listed here, we will discuss those in our machine learning course anyway. So the considerations are many machine learning models like decision trees, random forest, nearest neighbor Bayes, they are non-parametric, means they are not dependent on standard deviation, mean, and all that. And they assume a specific, they don't assume any specific distribution. So those models, for those models, we don't need to worry too much about normally distributed or non-normally distributed. But if we are using something like linear regression and so on and so forth, that requires the data to be normally distributed. So consider robust models. So we should choose machine learning models which are robust and they are less sensitive to outliers and some of the distributional assumptions. Examples like support vector machines or neural nets, for example, they can handle non-normality in the data as well. So we will talk about each of the machine learning models in our machine learning class, and we'll see which ones are the ones where we need to, take note of the abnormality in the data. Nonetheless, it's a good idea to experiment and study and understand the shape and distribution of the data, and make some good decisions based on which model will probably work for your data. That's pretty much in this topic. So this was pretty long 1 hour video. I thought I could wrap it up in 45 minutes or 40 minutes, but it went over 1 hour. Thank you all for your patience. We'll see you in the next video.